we still have one more kind of transformation to talk about, and that's in example 7 on our handout. And I've copied the relevant information here. And we're working with two functions, square root of x, that we're already familiar with. And the function we're comparing it to is 2 times the square root of x. So it's this multiplication by 2 that we want to think about. And so this is going to be our table of values for g. And I've already gone ahead and graphed our square root function that we're so familiar with. And so let's go ahead and figure out some of these values for g. So I'm going to use the same values of x. And for g, we get 2 times the square root of 0. Now 2 times 0 is 0. So notice we get exactly the same point. But for these other points, like when I do 2 times the square root of 1, that's 2. 2 times the square root of 2 is that, which is about 2.8. 2 times the square root of 3 is about 3.4. And 2 times the square root of 4 is 2 times 2, which is 4. 2 times the square root of 9 is 2 times 3, which is 6. And for negatives, we're still getting not defined. So the domain is actually the same here. The domain is not changed like it was for that other example we looked at. So let's go ahead and plot the g points down below. So 0, 0 is the same, but 1, 2 is different. And 2, 2.8, 3, 3.4. So this is 3.4 is about halfway. 4, I get 4. And then the only other one I did was 9, 6, which is going to be here on this scale. And what happens is I'm still getting this kind of like curves in a similar shape, but it's stretched out. And in fact, we call this a stretch. So it's kind of like we've shifted in a way, but see, there's not one single number of squares or number of spaces that we've shifted up. So a stretch means you're multiplying by a factor. Where you start out with a bigger value, the stretch is bigger. Where you start out with a smaller y value, the stretch will be smaller. And notice that 0, 0 is pinned down in this effect. It didn't move at all. And that's the way I actually think of that point as being pinned down. So when we try to stretch out, there's no shift at all. So how can we say this in words? Points on the graph of G are 2 times as high as the points on the graph of F. Or they're stretched away from the x-axis 2 times as far as the points on the graph of F. And I think our general statement is on the handout here. We can stretch or compress the graph of a function to obtain the graph of, now the difference here is I'm multiplying by some number a. And in here we say stretching and compressing. We stretch if a is greater than 1. So this is an example where the a value is 2. It's greater than 1. We're stretching. If the value of a is between 0 and 1, we're actually going to be compressing. And so for instance, if this were a 1/2 instead of a 2, I'd still have 0, 0 pinned down, but I'd have a graph that's pushed down a little bit closer to the x-axis, right, compressed. And I don't want to do another specific example of that. We're going to move right to our exercise. Now, if A were negative, we'll talk about that in the exercise. We're actually going to break that down into two separate operations. We're going to think of A first as being a positive, and then we're going to reflect when we apply the minus sign. But we'll look at that in the exercise, which will be a separate video.